Hello and welcome to another Java tutorial. In this tutorial, I'm going to look at the other good libraries for numerical integration in Java, and one of them that I highly recommend is the one from Michael Flanagan library. And it's just you search his name, Michael Flanagan, and he's a professor at UCL, University College London. And in his project flanagan.jar, you can just download the Java archive file from his personal website. There is a package called integration, all right? And basically we can divide the classes in this package in two parts. The first part is just numerically integrate a real valued function, all right? And very similar to what we did, it has an integral function interface. Now what we did actually was to divide an integral function interface for 1D functions, and then 2D functions and 3D functions. And then it has a class called integration, similar to what we had. So we defined a class called integral 1D, which integrated with different methods for one-dimensional functions. So this part, so there is this integration class, and then there is this integral function interface. So this part has an interface for defining function and a class for performing various integrations. And the part 2 is for solving differential equations, a system of ordinary differential equations. It has a deriv function. So if you want to solve y prime equals f of x and y, and we will look into the details of solving differential equations later in the course, but for now the deriv function is basically for solving y prime equals f of x and y. So the deriv function is an interface for implementing this f function. The deriv n function, so there is an n here, is when you have a system of n equations like this. So y prime of 1, y prime 2, y 3 prime, etc. equals f of x, y1, y2, etc. So you have n functions and n equations that define the first derivative of those n functions, which gives you n equations. So two interfaces for defining your system of equations, and one class called Rangakuta, which solves the differential equations using different methods. The most notable one is Rangakuta method, okay? And it's more like a fourth order interpolation of your differential equations, which is basically based on Richardson extrapolation, okay? So let's head to Eclipse and try to look at these two classes. So if you go to my MathLib class, in the referenced libraries, we have the Flanagan project. And here we have in the integration package, we have integral function, which is pretty much a functional interface that has only one public abstract method called double. And it's a function, and its parameter is a real double value function, and it returns a double value for the function. I mean, I wouldn't call it the method function, maybe the method value. So in our integral project, when we define the integral function 1D, we call it as value, which is I guess in my opinion it's a better name instead of having function as the name, okay? So and then in the integration class, and so let's quickly have a look at what method it has. It has a set limit, set lower limit, set lower limit, set upper limit, set Gauss-Legendre points, and set number of intervals, get integral sum, get integral mean, get integral standard deviation, get Gauss quad distances, get Gauss quad weights, Gauss quad. So it has a method Gauss quad for doing the Gauss quadrature, Gauss-Legendre quadrature integration, Gauss quad with a parameter of int, which I assume is the number of points, And then some static methods for go squad, coef, trapezium. This is the trapezoid method. Trapezium, get trapezium intervals. Backward, this is backward rectangle approximation. Forward, this is forward rectangle approximation, and that's it. So it doesn't have some of the methods that we implemented, like Simpson or center approximation, center rectangle approximation. So it's mostly based on the go squad and trapezoid. And again, when we discussed Richardson extrapolation, we said that you can in fact take any of these and put it on steroid by applying the Richardson extrapolation, which increases the rate of convergence. All right, so let's look more into the details of this class. So the class called integration, it has obviously an integral function which is initialized to null, has a Boolean set function, lower limit of the integration and upper limit, set limits false, Gauss-Legendre points, the default number of points for Gauss-Legendre is 0 points, set Gauss-Legendre points, number of intervals, the default is 0, set intervals, it's false, integral sum is by default 0, integral mean, integral standard deviation, and integration done, integration stats done, array list of integers, Gauss squad index, so it has an array list for Gauss squad index, array list of double, Gauss squad distance array list, Gauss squad distances, Gauss squad weight array list. So these are the weights, Gauss squad weight. So I guess the distances are just the roots of those points, the quadrature points. Gauss squad weights, Gauss-Legendre precision. So the default precision is 3 times 10 to the negative 11. Required accuracy default is 0. Trapezium accuracy is 0 by default. Trap accuracy, which is a static variable, and I guess this is going to be used in the static trapezoid method, because I guess the good thing that this guy has done is that for any instance method like Gauss squad or trapezoid, it also has defined a static variation. So you just call the class itself and pass in your integral function. For example, here's the static version of the trapezium, and you pass in your integral function, and then var1, var3, var5, var7. I assume that these are just the bounds of integration and some of the accuracy error, and then probably int is the number of subintervals or something like that. That's a good approach to have for any instance method. You also define a static variation, a static version of it. All right. The default number of intervals for trapezium or the trapezoid method is 1. All right. And it has a no-R constructor, public integration. Once you have a no-R constructor, obviously you have to add the setters and getters for all the parameters that you need. That's why all of these are set integral functions, set limits, var1, var3, lower limit, upper limit, set lower limit, and it also has flags for making sure that the limits have been set. So there's a set limits flag here, set lower limit, and then so it assigns the lower limit and checks the upper limit if it's nan, because the default for the limits are nan. If it's not nan, it means that the upper limit has also been set, so it changes the set limits flag to true. And then set upper limit, set lower limit, set upper limit. Yeah, these two seem to be exactly the same, so I assume this is a bug in the decompilation of the class. Yeah, similarly for the upper limit, it assigns the upper limit and then checks the lower limit. If the lower limit is not none, it means the lower limit has also been set, so it changes the set limits flag to true. Set Gauss-Legendre points, how many points we want for the Gauss-Legendre integration. In our implementation, we actually implemented for the Gauss-Legendre two default versions, 3 point and 5 points, and we said that 5 points is typically enough, and instead of increasing the number of points for the Gauss-Legendre, we divided the entire interval into some sub-intervals like 100, and then we performed 5 point Gauss-Legendre over each smaller sub-interval, and that's a faster approach in my opinion. Than it's definitely a faster approach than increasing the number of Gauss-Legendre points. But you can specify, if you are going to do Gauss-Legendre quadrature integration, you can specify how many points you want for Gauss-Legendre. And again, remember that this class, this implementation, doesn't break the interval into sub-intervals. So if you have a big interval, then you have to increase the number of points in order to get a good approximation. Set number of intervals, okay. I guess that the number of intervals is used for trapezoid. Let's go here. So the first occurrence of the number of intervals is here. Yes, it's in the trapezoid method. So it does, for Gauss-Legendre integration, it doesn't divide the interval, but you can set the number of points that you want, the number of quadrature points that you want for Gauss-Legendre integration. Set number of intervals, get integral sum, which just returns the integral sum, okay. Obviously it checks the flag for integration done, and if the integration is not done, it throws an illegal argument exception and says that no integration has been performed yet. And then another getter for get integral mean, the mean value of the integral, get integral standard deviation, and then there's an array, get Gauss-Legendre Gauss quadrature distances. These are the quadrature points. Gauss quad weights, these are the quadrature weights, Gauss quadrature, Gauss-Legendre weights. All right, so the distances here means the quadrature points. I call them quadrature points. And then it has the main Gauss quad method for performing Gauss quadrature integration, which takes no argument. So here it assumes that you have already set the number of Gauss-Legendre points. That's why right away it checks the set Gauss-Legendre points. And I'm assuming this was a flag. Yes, set Gauss-Legendre points a flag. When it by default is false, it means the number of Gauss-Legendre points has not been set. Now the problem here is that if you set it and then you change the number of points, then it still sets the flag to true, so there's no problem there. So if you haven't set the Gauss-Legendre, the number of Gauss-Legendre points, then it throws an exception, number of points not set. Else if the limits is not set, it throws a new illegal argument exception, one limit or both limits not set. If the integral function is not set, it throws a new illegal argument exception, no integral function has been set. And if all of these are satisfied, and then it sets creates an array. Gauss quad distance is basically the quadrature points, and then an array for quadrature weights, and then var1 true, var2 -1. Gauss quad index is empty. So what was this one? This was an array of an array list of Gauss quadrature in integer, array list of integers. for var3 equals 0, var3 less than go squad index dot size var3 plus plus integer, this go to get var3, var4 equals this goes Lejeune points. So basically what happens here, and then var1, var1 is false, var2 equals 3, so it has a flag var1, and then go squad index, go squad distance array list, again weights, again these are all for getting the yeah, these are just for getting the weights, calculating the weights and quadrature points. So let me see where this happens. So the go squad index is initially empty. Okay, and then integer, this goes Lejeune points. Okay, goes squad list, double this goes squad distance array list and weight array list, and it returns a okay. So this is all for calculating the go squad quadrature points and weights, and here's where the actual integration happens, which is just a summation, right? We have to be careful about the scaling. So here this is 0, half of the upper limit, lower limit over 2, var7 is upper limit minus lower limit over 2, and again, in order to refresh your memory what these scalings are, I'm going to go back to the when we looked at the Gauss Legendre, and we said that Gauss quadrature method is only defined based on the Legendre polynomials over the -1 to 1 interval. So if I want to calculate from A to B, I have to do a mapping to map this integral to -1 to 1. All right, and then the coefficients of this mapping are upper limit minus lower limit divided by 2, upper limit plus lower limit divided by 2. Okay, and then here, so my new function that actually goes into the -1 to 1 to integral if the original function b minus a over 2 times x plus b plus a over 2, and here x is between -1 to 1. So I calculate this new g of x using the Gauss Legendre. So basically this integral becomes sigma of I from 1 to n wi g of xi, and xi are quadrature points which are between -1 to 1, and wi's are quadrature weights. And then when I calculate this, I have to scale it again, b minus a over 2. And also I mentioned that this is where obviously we see that the error of the integration also scales linearly with the length of the interval. That's why if we are integrating over a larger interval, we have to have a better or have to have a smaller error. So that's why we need to increase the number of points, quadrature points, as we increase the size of the interval. Otherwise, then the error gets also scaled with this factor, and that's not good. All right, so here are the two coefficients, half of the upper limit plus lower limit, half of the upper limit minus lower limit, and I assume var9 is basically one of these two is keeps track of the integral. So var11 0, number of Gauss Legendre points plus plus, remember we need to multiply the weight. Okay, so var7 is the scaling factor, upper limit minus lower limit over 2 times Gauss quad distance, and So this is basically scaling the quadrature points. Remember the mapping, it was b minus a over 2, this var7 times the quadrature point, and plus this var5, right? So this multiplies that creates var9 goes quad weight times this integral function var5, which is the b plus a over 2 plus var9, which is b minus a over 2 times the quadrature point. Okay, so this calculates the integral function at the so basically it calculates the integral function at b minus a over 2 times the quadrature point plus b plus a over 2, and does the summation for all the number of quadrature points, and when it calculates the sum, then it multiplies by this scaling factor b minus a. Again, var7 is b minus a over 2. All right, and then integration done, it sets the integral sum and then returns the integral sum. All right, so the only thing here is how it calculates the quadrature points, quadrature distance, and quadrature weight. Obviously this is a more efficient way of doing it, and you can look it up on Google or on the algorithms to actually do to find the quadrature points and quadrature weights. The way I did it, I just simply said that okay, these are the roots of the quadrature points are roots of the Legendre polynomial, and quadrature weights are related to the derivative of the Legendre polynomial. So I calculated them that way, which is not a very efficient way, obviously, especially if the degree of the Legendre polynomial is very large. So this is a better way of doing it. Okay. All right. So, and it has another method, goes quad, with an parameter, integer parameter, which defines the number of Gauss Legendre points, right? So if you call this and pass in some integer, it sets the Gauss Legendre points to this parameter, set Gauss Legendre points, this flag to true, and then calls the Gauss quad with no argument. And it also has a static method for Gauss quad, integral function, double var1, var3, which are the limits of the integration, upper limit, lower limit, and then the integer var5 is the number of Gauss Legendre points. So it creates a class integration and calls one of the constructors, which takes the integral function, lower limit, upper limit, and then calls this on this class calls the Gauss quad method, which takes the number of Gauss Legendre points and returns the result. And then it has another method for doing the integration, but it returns an array list of double values, and it returns the Gauss quad integration plus the mean value of the integration and the standard deviation. And again, I'm not going to go into the details of how the what is the standard deviation of the integral. But there are approximate equations that you can again search for them on Google to see how we can define the estimated error, which is basically the standard deviation, and then for the Gauss quadrature method. And we have also a static version of this method, and then Gauss quad coefficients. So this public method basically returns the Gauss quadrature coefficients, and then so these are based on the Legendre polynomials, and again this is a relatively efficient algorithm for calculating the Gauss quad coefficients, the quadrature points and weights. And in this class, the quadrature points are called quadrature distances and the weights are called quadrature weights. So you can just use this one to just calculate the basically this doesn't return anything, it's a void function, and it just populates the Gauss quad distances and Gauss quadrature weights. And then we also have a static version of that. So you pass in two arrays and the number and then it populates the Gauss quadrature points, Gauss quadrature weights, and I assume int here is the number of Gauss-Legendre points, right? So it creates an integration object and then sets the Gauss quad coef var2. So it's basically here, int var1 is the number of points, and then var0 is get Gauss quad distances. So you can invoke this method to get the quadrature points. var1 is var3 Gauss quadrature weights, so this returns the Gauss quadrature weights. That's it. So again, for Gauss quadrature integration, all we need to do, we need to get the weights and the quadrature points. Once we have them, we have to take the quadrature points, which are always between minus 1 to 1, and map them to a point using this mapping that is between a and b, because the integral function is going to calculate at those points. Okay, and once we do that, we calculate this sum, and again we have to scale it back from b minus a over 2 to find the correct value for the integral. And again, because of this scaling factor b minus a over 2, the error of the Gauss quad also linearly scales up with this factor, which is not good at all when the interval is very large, or b minus a over 2 is a large factor. That's why you need to reduce the original error by increasing the number of Gauss-Legendre points. So the next one is the trapezoid method, which is pretty simple. Trapezoid is breaks the interval into some number of subintervals, right? Set intervals is basically the flag for making sure the number of subintervals is set, and then integral function, it evaluates at the point. Integral sum plus equals half of the initial point plus the end point, and then it just adds them up and then returns the integral sum. And if we call the trapezoid method with some integer parameter, it just sets the number of subintervals to this parameter. We also have a static version of the trapezoid method, and then we have a trapezoid method based on the required accuracy and then the number of subintervals or max subintervals. So this is more like an adaptive approach. You set the accuracy and the max number of subintervals. And I assumed it starts with some low number of subintervals and increases the number of subintervals, and with some increment, and then checks when the accuracy is reached. So this is one way of doing that. We have a static version here. Get trapezium intervals. This just returns the intervals accuracy. This is the rectangle backward integration, right? It just takes the value of the function times the length of the subinterval, and then backward with some integer parameter, which is the number of subintervals, a static version of the backward. Forward, I'm surprised that it doesn't have the center approximation. So again, for forward, you calculate the function at the beginning of each subinterval multiplied by the length of the subinterval, which is again uniform partitioning. For rectangle approximation, we always assume uniform partitioning, upper limit minus lower limit divided by the number of subintervals, and we have static versions of those. Yeah, so this is a very good class. It doesn't have the Simpson method, but it has very good and I assume very fast Gauss quadrature approach, and the trapezoid and forward and backward integration. So I highly recommend you to use this class also whenever you can. and it's in the Flanagan library in the integration package. So you first define your integration function as a functional interface and then pass it to the integration class. I hope you enjoyed this video, and I'll see you in the next one.